The more organizations claim to be data-driven, the less critically they actually think. We have become entangled with automation and efficiency. Analysts and executives routinely look at highly polished dashboards and treat the numbers they see as absolute facts. But those outputs are not facts. They are automated hypotheses generated by systems executing predefined rules. Evidence does not speak, it must be spoken for. Every dataset you encounter is a highly curated artifact. It reflects very specific human choices about what to measure, what to select, and exactly what to ignore. To restore the balance between human reasoning and automated inference, we must deconstruct the specific cognitive and logical errors that disguise random coincidence as causal truth. Human reasoning has to intervene exactly where algorithmic computation ends, separating automated complacency from justified knowledge. Before any relationship between variables is analyzed, we have to practice epistemic hygiene. Epistemic hygiene is the continuous verification process of ensuring data actually deserves analytical trust. We have to question the data itself. This flowchart illustrates the two pillars of analytical trust. Reliability concerns consistency, producing stable, repeatable readings. Validity concerns truth, measuring the real-world phenomenon. Imagine a broken sensor delivering precise errors. It demonstrates perfect reliability, yet total invalidity. The result is entirely false. Algorithms naturally optimize for this kind of consistency because reliability is mathematically easier to achieve and measure than truth. It is solely the human analyst's responsibility to enforce validity through critical interpretation and contextual understanding. Data reliability without validity yields nothing more than precision without truth. As analytical systems scale, data volume actively amplifies the likelihood of spurious connections. The sheer amount of variables guarantees that unrelated data points will eventually align by chance. This matrix breaks down relationships analysts constantly conflate. Correlation describes a consistent association, but proves no underlying mechanism. Causation demands temporal precedence and a definable mechanism proven by logic. Coincidence is mere simultaneity, events occurring together by chance, an inevitable outcome in massive datasets. To see what happens when these definitions blur, consider a behavioral analytics case from a major e-commerce platform. Executives assumed a direct causal loop. Viewing luxury goods drove customers to spend more. Flooding the homepage with luxury products caused overall sales to plummet. The true mechanism was reverse causality. High-spending customers naturally seek premium sections. The items merely described an existing behavior. Intervening based on misread causality, treating a descriptive behavior as a functional cause, directly manufactures self-inflicted corporate loss. Logical fallacies are particularly dangerous in analytics because they violate the strict structure of reasoning while completely maintaining the illusion of numerical precision. This diagram illustrates the cognitive traps that distort interpretation. The ecological fallacy uses aggregate data to infer individual behavior. Base rate neglect focuses on conditional warning signs while ignoring underlying probability. False causation links simultaneous events without a defensible mechanism. When an analyst codes a flawed premise into a machine learning model, the error scales exponentially. The algorithm mechanizes the fallacy. These mechanized errors are then compounded by structural institutional bias, where organizations intentionally or unintentionally weaponize these fallacies. Watch data degrade flowing through management layers. At the analyst level, data is complex and noisy. As it rises, authority bias takes hold. Models are tuned to confirm preconceptions, stripping away error margins. At the executive level, nuance is erased, replaced by a simple binary indicator. Institutional pressure prioritizes group cohesion and reporting convenience over accuracy. It erases the necessary discomfort of uncertainty, turning analytical inquiry into corporate propaganda. The only viable defense against this automated complacency is the strict implementation of procedural skepticism. Proper analytical reasoning requires you to actively define the explicit boundaries of inference. You must declare exactly where your conclusions are valid by setting strict temporal scopes, contextual assumptions, and falsification thresholds. For example, a predictive credit risk model trained on financial data from a stable European market might be highly accurate locally. But apply that same model during a recession or a different regulatory regime, and its logic collapses. A documented boundary protects your reasoning from out-of-domain extrapolation. It prevents users from applying findings to environments where underlying assumptions no longer hold. All analytical relationships decay, market structures evolve, and behavior shift, meaning there is no such thing as a timeless analytical model. Declaring exactly where your model fails is not a weakness. It is the ultimate mark of analytical rigor and professional integrity. The true role of the modern data professional has changed. Your job is no longer to outcalculate the algorithm. Your job is to outreason it. We must preserve data as a tool for rigorous, skeptical inquiry, rather than allowing it to become an automated mechanism for institutional denial.